Alright, time for another draftphysics.com, debatephysics.com, also video presentation. So, I will try not to swear or do anything, you know, to bother somebody in some dramatic way, as if this is just so difficult. Trying to challenge the conventional belief memes, and they're just so defensive. So they're supposed to be scientists, physicists, but they're really not very scientific. And so you have to, almost do this little kid thing. So anyway, I found this channel of these two women, and they're doing pretty much the same stuff that's already on the internet in about a million forms. So I don't know why they all choose to teach physics, and they're all teaching exactly the same crud. And instead of doing some physics, like demonstrating something with some unique experiment or something, but there's really no added value. So anyway, except that they're girls doing physics instead of some Indian guy, frankly, because that's all there is on the internet. It's just so bad that YouTube lets this happen. So I'll a little bit of a sidetrack just to go through this. I mean, you can't look for physics channels on YouTube. It's just idiotic. So there's the two girls. Everything else is this stupid Hindi crap, and they put an American title on it and pretend it's not Hindi crap. And I'm sorry, I don't mean, I got nothing against, but it's lying. It's just a deception. They're trying to get views, blah, 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 blah. Get people to click on their crappy videos that are incomprehensible to an English speaker, and yet it's all written in English. That's bullshit. Ah, there's one. Okay, so we got an American somewhere. We got an English speaker. Okay, so I'll have to check that one out. But I mean, it's just 80% are in Hindi, so it's really bad. So there's a little better. See, we got 4 in a row there. This was just random, but I'm just saying I can show you plenty in Hindi. Okay, and even when there's some English, all these really low view ones are in English, so that's surprising. All right, so let's go up to the higher view ones, and then you'll see my point. Because all of them won't be in English. Okay, so see, not in English. That one's in English. I saw that one. That one's in English, so I'm going to actually make a response to that one. Oh, but that's obviously not in English. This one is going to obviously not be... Oh, it's in English. Okay. This is crap, so it doesn't matter whether it's in English or not because it's crap. But anyway, they're not in English. I'm just saying that, it's... Look, this will be 1, 2, 3... 4 in a row that won't be English, and that's 4. Let's see what this one is. 5. So we got 5 in a row. 6. This will be number 6 in a row. Not English. Not English. You can see my point. Not English. 7 in a row. All right, there's English. Maybe. Now I listen to that guy. He's mostly, you can sort of understand him. So that's 8 for 9. Come on. DVR Academy. Alright, we'll assume, I don't know, the icon doesn't look too good, but, oh, no, not English. So, it goes on and on. So you're talking 12 to 1, 15 to 1, all not English speaking videos. So what's the point? I'm just saying, it's idiotic for the search mechanism to allow that kind of deception. I mean, they should give you a filter that says English. I want English videos. I don't want videos in a foreign language. It's of no value to me. I'm going to watch a video. I do not want to have to translate the the text. I mean, come on. It's just nonsense. Anyway, it's just part of the broken, stupid, idiotic internet. All right, so let's get on to the real subject here. I could have done this video, but I didn't, and decided to do this one instead. Introduction to forces and Newton's laws. And it just, I might as well just play the video, and I'll just make the simple points that, why, you don't want to be teaching kids, okay, nonsense, and that's what I think you're teaching them. And you also don't want to be dissing Isaac Newton, and that's what you're doing. Because he didn't say what you're saying he said, okay, and it wasn't his physics. It didn't follow his logic or his understanding of how the thing worked. And so you're just, kind of lying. And you ought to not want to be a liar. I mean, it's not a nice thing to be a liar. Alright, so let me do this with that volume thing. Should have done that. Oh, it's already done for me. Yay. And we'll do this pop-out window thing. So I better pause, because who knows if that'll work. No, apparently it did. Alright, so let's play the video and see where we go.
Hi, I'm Beth.
And I'm Beth.
Welcome to Physics with Beth
and Beth.
Hey, we are on AP Physics 1.
So, this is just my own opinion that, somebody interested in physics isn't really going to be interested in all that little kind of, personal fun stuff. We're friends, we have the same name, it's really cool. Yeah, no. Just a moment. Alright, back and such.
We are on Unit 2. This is our first video on Unit 2. So yay, you've made it to Unit 2. Way to go. It's about dynamics, and it's really about, dynamics is a big fancy word in physics. It just means forces, Newton's laws of motion. We're going to be talking about that in this unit.
Right, and so everybody on the, sold me about 500,000 videos, I don't know. If you count the Hindi ones, there's a trillion videos. But anyway, go ahead.
So hopefully you survived Unit 1 and we're pumped and ready to go for Unit 2. Here we go. We're just going to start with Newton's 3 laws of motion. All right, by the way, before I even start on this, I just want a little tidbit. I was just so fortunate enough to win a fellowship to study the history of Newton's life and went over to Europe and at his estate. I find it really interesting. Sometimes it's nice to put a picture, a mental picture of somebody instead of just seeing a name. He was on an estate with a little river that ran by his home, as well as an apple tree. It's a myth whether he really saw an apple fall or not and started making...
Well, whatever. It's a story he actually told, okay, in interviews very late in his life. So, yeah, it's probably something he made up, just to make it all sound more charming. But anyway, who cares? I won't say that. The point is you went all the way to Newton's home, and what you're going to say about what Newton's physics is so wrong, and not his physics, and actually the physics of his worst enemy in life. And, you should know that. You should be somewhere along the line. I mean, before they send you to Europe, you should know who Isaac Newton was and what he said. And he didn't believe, okay, that it took 4 times the force to move something twice as fast. And he didn't believe it took 3 times the force to move something 3 times as fast. 9 times the force to move something 3 times as fast. And he didn't think it took 16 times the force to move something 4 times as fast, and you think it took 25 times the force to move something 5 times as fast. That's Leibniz's physics. That's the junk kinetic energy theorem that you're going to basically put in Newton's mouth, and it's not his physics. He said twice the force, twice the motion. 3 times the force, 3 times the motion. He went to the trouble, because you might not have gotten it the first time when he said twice equals 2. He went there one step further and said 3 equals 3. And you're going to sit here and tell me he said something different.
That thinking of why did that happen, but it's true he did have an apple tree, and actually a few generations later of that apple tree is still there on his estate. But he used that river and studying with rocks and water and just nature around him, started studying these laws of motion, and also wanted to he just thought Galileo was the guy, and wanted to continue his work as well. So anyway, interesting.
Right, and Galileo, Descartes, and Newton all kind of understood this idea of quantity of motion, so they understood the motion was basically just exchanged among objects. And that's how the motion moved through the universe, that there's a certain amount of energy in the universe, and the energy just moves from one object to another object to another object to another object in these subtle and different ways. Now, they didn't have it all put together in the sense that I don't think they really understood that heat is actually motion, where we do understand that heat is motion, that it moves through objects, that it's got all the properties of being the same thing as momentum, just very small things are doing the moving.
Enough. So we're going to talk about this first law. Hopefully you've seen some of this, maybe in elementary school or junior high, you've at least seen some of it. We're going to take it up a whole big level.
Yeah, it's really not, no, it's going to happen.
In this unit in AP Physics 1, as you would expect. But anyway, let's start with Newton's first law. His first law says that an object at rest will remain at rest, and an object in motion will remain in motion at constant velocity unless acted on by an unbalanced.
So you'll keep whatever money you have, okay, until something happens to change how much money you have. Either somebody gives you more money, you steal the money, but that's how it works. So whatever condition you're in, you're going to stay in that condition until something changes your condition. And there's no resistance to you getting your condition changed. There's no such thing as some sort of inertia problem. There's just the problem of I have to hit something, or I have to have contact with something to make exchanges. We can't exchange what we have through no medium. We have to do it through a medium. So I could send a bunch of photons, or I could spit at you, or I could throw a bowling ball at you. So there's lots of ways I can exchange my motion for your motion, my energy for your energy. But it's always an exchange. If you get $10 richer after we hit each other, then there's every likelihood that I'm $10 poorer. That's how it works. It's just a currency. Quantity of motion could just be called quantity of money. It could just be called quantity of gold. It could just be understood as quantity of water. It could be understood as just a substance, like something you have, and you give it, okay, or something else takes it by rubbing up against you in some way.
Force. Now, what you might have heard before was an object at rest will remain at rest unless acted on by a force. Well, when you say it like that, you're missing some key components there.
No, you're really not. I mean, it's all you need to know, because there's no way to be acted on forces. I mean, you could say until acted on forces, but Newton didn't say forces because, yeah, you could have two forces that are acting on you in opposite ways, and it might look like there's nothing happening, but of course there's something happening.
First of all, remain at rest or will remain in motion at a constant velocity unless acted on by an unbalanced force. You can have forces acting on an object. In other words, if I have this little bunny and I push on it from both sides.
So yes, if you push on it from both sides, do you think nothing's happening? I mean, do you really think there's nothing happening? I mean, if we had a thermal camera, right, what we'd see is we'd see this thing's getting hot, because your fingers are going to take in the pressure. The object itself is going to be under stress, and it's going to get warm. So you're going to actually heat it like you would heat a rubber band or something else. It's going to actually be a thermal consequence, because you can't cancel energy. This side can't cancel that side. If they were, if it was a Newton's cradle, okay, and you have two steel balls and you let them bounce off of each other, no substantial heat will be created. But if you crash them together and force them not to rebound, then you know all the energy is still in there. So you stop them from moving. It looks like nothing's happening, but the fact is they'll generate enough heat to actually start a fire, to actually burn a piece of paper. Those are the facts. The fact is the energy, it's lots of stuff going on inside of that molecularly. You're stressing the heck out of it. A lot of stuff is moving about, just as when we crash into the ground, okay, every millisecond we're being pushed into the ground, and the ground is pushing us back up. And if we had a thermal camera and we could shine it on my ass is going to be warmer than the rest of my body, because there's a lot of action happening there. There's a lot of transactions. The force gives the ground $10. The ground gives me back $10. The force gives $10. The ground gives me back $10. There's lots of transactions of energy going on. And all of that energy has to go somewhere. For every transaction, it doesn't just end. It has to go somewhere.
It's still at rest. It's not moving. And I have
the constant force of gravity either heats the center of the earth, it heats some other portion of the earth, it heats my ass, or it heats the air. But it has to go somewhere. There's no stalemates, true stalemates in physics. If you have a constant force, there has to be a constant radiation of that force. It has to be constantly radiating out of the object if the object isn't moving and you're hitting it with a constant force. Because again, as Descartes gave you this simple diagram of just understanding that there's energy in, the system is initiated, there's little units, there's a certain units of energy, certain little Planck units of energy are in the universe, and all you're doing is saying, who's got them? The stuff moving has them. It's just a fact. And it has an imbalance in them. Okay, that's the truth of it. Because it can have, I can have a million units of energy, and yeah, some of them are going this way and some of them are going this way. And for my whole system to move, I need more of them going this way than are going that way. But obviously for individual objects inside of me, they can only go this way, or they cannot be moving, or they can be going that way. There's only 3 states that an electron can be in. It's going that way. And that's for all 3 dimensions. It's standing still, or it's going that way. But there's no other state it can be in.
Force is acting on it. I'm pushing from both sides. But the bunny's not moving. All right? So it's not, so it's an unbalanced force. Once I put it...
Yeah, so, but again, you're just cheating the argument to imply that there can be a constant force on something, and it doesn't have to constantly radiate that force somewhere if you don't see anything moving. The force still has to be going somewhere.
In my hand, and I push, it's at rest, and I push and it accelerates, it gets faster and faster and faster and changes its velocity. Now I have an unbalanced force, and it will not remain at rest, or it will not remain with a constant velocity. All right, now when we talk about a force, this is the first time force comes up for us. What is a force? A force is just a push.
Force is just momentum, and that's sort of what Newton made kind of clear when he said, okay, twice the force, twice the motion, 3 times the force, 3 times the motion. He's just saying there's clearly an equality, okay, between the magnitude of your velocity and the force applied. And that relationship essentially is just saying force is momentum. It'll give you momentum. It will proportionally change your velocity as long as you leave the masses. If you change the mass, then obviously that changes the equation, but the force will increase your velocity proportional to that change in mass, if you're going to include mass. But the simple argument is that it's basically an equivalency. Twice 2 equals 2. You can't deny the equivalency. He's drawing between the change in your momentum and the force. So you might as well consider the force to be momentum. It's just in a different form. So you can have momentum in a bunch of laser photons, or you can have momentum in the form of this pen. I could throw it. Or you can have momentum and I throw the pen and you catch it. Lots of different ways to collect and reject force.
Or a pull. That's all it is. And we're going to...
So the thing to be understood, I think the argument should be made, is that the force and the idea of momentum are equivalent. So if you think of momentum, you should be thinking about the force that caused the motion. And if you're thinking about some external force, like photons or something, think about the fact that there's the same motion, except it's in an object that's in little pieces. There's the same mass and velocity hitting you. It's just not in a consolidated form, so you don't see it as an object, but it might as well be one. It's exactly the same thing. It doesn't matter. It's like I break the earth into a bunch of little tiny separate atoms and I, quadruple its size or something. They're still going to go around the sun exactly as if I hadn't done that. It's the same stuff. It's just in a form that you can't see, but it's still momentum. It's still just little bits of stuff moving.
to talk about different types of forces, but they all just push or pull.
So push, again, this is elementary physics, and I don't think you should be fooling a kid by saying anything other than, look, children, okay, push is really easy. Banging into something and making it move. So you can bang into it elastically and bounce off and it moves, right? But we know you can't have it both ways. You can't give your $10 and then keep your $10. You know, and motion, direction doesn't make any difference. Motion in the universe is momentum. That's energy. Two things moving, two pens moving is more energy than one pen moving. And certainly one pen moving twice as fast as what I started with would be ludicrous. So you shouldn't be teaching that nonsense physics. But that's all there really is. You have the interaction, and you have to conserve the amount of motion that's in the universe. So you can't make free motion, ever. Mass moving. The total MV can never change anywhere. So I could quote Professor Lewin, you know, you can, what does he say? Shit, I gotta remember the exact words. You can deal with kinetic energy one way or the other, but you can't finagle momentum.
And we've got a couple videos.
Nature can deal with kinetic energy one way or the other, but nature can't finagle momentum. That should be part of these three laws, the context of them. So Newton didn't have, you know, none of these laws are really pure conservation laws. But clearly it's an easy enough conclusion to draw that that's the same universe that Galileo and Descartes saw was one where the energy is conserved.
Coming up, a catalog of forces that are going to tell you about the different forces, the equations you're going to use for.
So again, there's really no different forces. There's just different things moving. So a photon is a thing. It's moving, the speed of light. The thing that the photons that cause magnetism, they're things moving. Everything is a thing moving. Okay, so there's no such thing as different kinds of force. There's different kinds of objects. We're made out of cells. We're first made out of organs, and then we're made out of different kinds of cells, and then we're made out of different kinds of chemicals. So you can break it down and understand that, yes, okay, you have to have the constituent chemicals to make the organ. You can't just, you know, you have to have the atoms before you can get to some other composition of atoms.
These and the strategies behind them, but I'll always think that know that a force is a.
So again, force is a push. It's always a push, and the way you just illustrated, where you had two things pushing, you take one of the pushes away, and the thing goes. So it's kind of obvious that, yeah, okay, push works. Push works to create the illusion of a pull. Because, yeah, all you have to do is have equal pushes, and you just remove a push, and you have what looks like a pull. And so you should tell kids that pull, some concept that one thing is here, one thing is here, and without any pushing mechanism, I can make these two things attract. That I can't do. I have to have a pushing mechanism. And the fact is that's what gravity is, and that's what magnetism is a mechanism that actually does allow you to push them from the outside, because you negate the force on the inside. The earth absorbs energy, gets really hot, okay, and that's why you get pushed into the earth. It's because the energy coming from above you has not been diluted by the earth, stealing it. So there's more pressure pushing you this way than there is pressure pushing you up this way, because of the fact that you're heating the earth with the difference. You're fueling the earth's fire. The earth's fire can't just, you don't start a fire 10,000 years ago and it still burns. There's no eternal flames. Flames have to be constantly fueled. The molten center of the earth has to be constantly fueled by energy. And that's the energy you don't see at the surface. That's the energy that's missing when you're sitting on the surface of Earth. And you're just getting pushed, okay, because you've eliminated the balancing force from the rest of the universe. You've blocked by putting a big Earth in the way. So you can visualize it as being light. So if the force was photons of visible light, you could understand, you can see lots of light up and you don't see any light down. So yes, you're in a huge differential. Simple explanation. Now yes, it has consequences. Newton endorsed the idea for a while of a particle gravity. And it's just he didn't have an answer for the thermodynamic problem in complete form because he didn't understand thermodynamics completely. But it can be understood in the sense of the whole problem of drag can be understood that electrons and protons, the elemental bits of matter, are in fact dragged. It does happen. They can't be shot to the moon. You can't shoot electrons to the moon. You can't shoot protons to the moon. You need something as big as a helium nucleus. That you can shoot to the moon.
Push or a pull. Okay? Now, in a car, let's say you're going down the road at 60 miles per hour. All this first law really says is things just want to stay the way they are. If you're at rest in the morning and your alarm goes off to go to school, you really just want to stay at rest, usually, right? Objects just want to stay the way they are.
So I'm just saying, I think this is the wrong way to teach physics, is that everything has a condition and you have to have contact to change the condition. There has to be some way for you to communicate the change. So the wind can do it in an invisible way, but you know, we kind of can feel it and sense it. And gravity just works in a way where all of our pieces are moved evenly so we don't feel it. But most all of the other forces, there's no other force, I don't think, besides magnetism, but we're not very magnetic, so that doesn't work great unless you want to risk your health. You're not going to be exposed to enough magnetism to give you a sense of acceleration or deceleration without your whole body feeling it. And it's probably going to be the pieces of you are more magnetic than others, and so there will be a bunch of irregular motion. So gravity is a completely different force because, yes, it can act on you without you feeling it. But all the other ones are going to be contact forces, and you'd have to have contact with something before you could be moved by it.
That's what it's called. We actually nicknamed this the law of inertia.
So that's just totally wrong. There's no resistance to motion. Nothing resists being moved. Nothing resists you giving it $10. So everything is saying, go ahead, give me some energy. I'll take it. So give it to me, and I'll go. So that's all there is. There's no inertia. The fact that big things need a lot of money to move, okay, the fact that a little tiny, a drop of gasoline won't be able to move a Mack truck, well, duh, okay, so, but that's not because the truck is saying, I won't move. The truck's just saying, as a practical matter, I can't move unless you give me enough energy to move. All right, there's a minimum amount for me to push all of the matter I have. I have 1,000 things I got to move. All right, and you have to give me enough food or energy or fuel to move those 1,000 things. And if you just give me enough to move one of them or 10 of them, well, I'm not going to be able to move. And I'll just give you back your money. I'll just reflect whatever you throw at me.
Inertia meaning, let me write that word down, inertia.
So just a made-up concept doesn't really exist. So this is like their scalar vector talk. The scalar is just absolute wishy-washy, mushy idea of some kind of speed thing that doesn't know which way it's going. So it has a magnitude, but it doesn't have any motion in a direction. So it's motion without a direction that has a magnitude, a strength. So you have a strength of motion, but you don't have any direction. I mean, it's just absolute babble and nonsense. And this word was again invented for no practical purpose, in the sense that you don't need to have any concept of resistance. You just have to know that you have to put water in a bucket for the bucket to have water in it.
Meaning a resistance to change in motion. Things just want to go the way they want. They want to resist changing.
Okay, so there isn't any. That's just the wrong way to teach it. Nothing's fighting it. Things are saying, give me the energy. And there's just certain rules about how you give it to something. And if you're going to give it in a form they can't absorb, you're going to get your energy back. The money, if I give it a Canadian money or I give it some other frickin' currency, it can't cash that, it can't use that. You have to give the currency in a form it can accept. Just
in
like the
motion.
science has to be in English or it's not of any value to me because that's the only language I speak.
So let's say that you're going down the road at 60 miles per hour. Your car is going 60 miles per hour.
Right, so you already got accelerated by the seat of the car. So the seat of the car was attached to the car seat pushed you, got you up to 60 miles an hour. Now you're going 60 miles an hour, but you're still stuck in the sense that there are some forces that add some resistance, but it's really tiny because you're protected from the wind. So you don't have to worry about air resistance. You don't have to worry about lots of things because the air is going with you. So you're pretty insulated from the world for a little while. But if the car changes, then you're going to have to change because things are going to start changing in terms of your position in the car relative to everything else.
See on a highway, you see cars in front of you braking, you hit your brake, your car is now slowing down, but your body is a thing in motion and it wants to just stay in motion at 60 miles per hour.
There's nothing to take it away yet because you haven't had contact with something, all right, that can push on you. You're trying to do the pull thing, right? Your seat is stopping and you're going. Your seat can't pull you back to the seat, right? There's no pulling force. You need something to push you back into your seat.
Without a seatbelt, it will hit the steering wheel or the windshield at 60 miles per hour because that's how it wants to stay.
But we know that the car ain't going to stop that short, and we know, lots of other things. So it's not going to be 60, it's going to be 40 or some other derivative of the total velocity. And clearly it depends on how much your body yields. So you're also going to resist moving. So even the fact that you're sitting, you have at least your gravitational friction to the earth. You have some things that are keeping you where you are. And so parts of you will move and other parts of you, your skeleton, will try to resist that motion. So yeah, you'll have some capacity to brake that's internal.
That's why seatbelts are so important. If you learn
Oh, yes, mother.
nothing from this forces unit, you
It's just, I just need another nagging mother.
learn that you
Yeah.
need to wear your seatbelt.
Yeah.
All right, but the seatbelt ties you to the car. So now it will help your body stop at the same rate as your car.
Right, but you don't want to stop at the same rate the car's stopping. You want to stop even slower than that. So, better yet, instead of an airbag would be just a spring, and a compression plate that just fit you just right, and you could just put your spring on the dashboard, and then if you hit something, get a nice little spring back, no problem. So yeah, there's lots of ways that we could do a better job of protecting ourselves, I would argue. But we don't, because we're humans.
Car. It will help you slow down. All right, and the airbag will as well, but anyway, hopefully you never have to use one of those. All right, so that's all that is. The law of inertia, or the first law of physics, says that an object at rest will stay at rest, or an object in motion will stay at a constant velocity unless acted on by that unbalanced force, that push or pull.
Push. There's just no pull. So again, it's really elemental, I think, for some kid to understand that there's no rational elemental pull. That's magic. Pull. It's magic. There's no way to make a pull out of simple objects. Simple objects can't have arms and they grab something and then they pull it in, and there's none of that. So the elemental universe can't be made out of anything called pull. It has to be made out of inverted pushes. You have to only manipulate the push. I mean, I can use the analogy to other things like a positive and a negative. All you need is the negative, and then taking away the negative creates the positive. So all you can do is, you can make holes into the ground and fill the hole. So you can argue that all you need is the negative force, and you can have the illusion of the positive force.
All right, second law. Second law, your ma is a force to be dealt with.
Oh, brother. So she has to do it again. I wonder how many kids that appeals to. It certainly doesn't appeal to this adult, anyway. So whatever this squiggly thing is, I guess she's saying that means net force. So this isn't the net force formula. It's not what Newton wrote. It's not Newton's mechanics. So Newton simply said force, big F, equals the change in your momentum over, if you choose, an amount of time. So if you want to know the rate, as in gravity, he stated it was 32 feet per 1 second. So it's 32 feet of added, let's see, how did he put it exactly? You know, of distance added to your velocity per second. And so, you know, in that context, then you might want a rate, like 9.8 meters per 1 second. All right. Or per second, which is still a 1, per 1 second. It's always in 1 second units. It's not in second squared units. It's not in multiple second units. It's in 1 second units. Every 1 second you get 9.8. There's no other seconds, just the 1. All right, and so, you know, they pervert that. They pervert this into that, and then that into Leibniz's theory. So instead of accepting the first sentence under Newton's second law, so the first sentence he wrote, after writing that, look, the force applied is proportional to the force received. I mean, the motion received, which is the second law. He states twice. You want to go twice as fast, twice the force. You want to go 3 times as fast, 3 times the force. And this is what they perverted it into. So what he's, you know, I'm just saying, if you take Newton's formula, F equals the change in your momentum over time, and you say, I want to know the net force. That is, after everything happens, what's the net effect? Well, then you just cross the time out, because the time becomes a 1 unit of time, the net amount of time, the total time. And it's just 1 unit of total time, so you know that it's really just F equals the change in your momentum. So the force you applied will equal whatever the change in your momentum is. If you're going 3 times faster, then you put 3 times the force in. If you're going 7 times faster, you put 7 times the force in. Force equals the change in your momentum. Force is momentum. The force is in newtons, you know, which is just more nonsense. But anyway, you know, because they square the seconds in the description of a newton. But a newton is just 100 grams. It's just a pressure. You're just applying a weight to something.
Is one of the sayings to help you remember that. But all it's saying is the sum of the forces, or the...
So it's not the sum of the forces, none of that. There's no, I don't know how you can change this into, oh, we're talking about a bunch of forces and time is somehow relevant. No, time isn't relevant then. It's just what's the total change in your momentum. That's the total net amount of force you got hit by in different directions. But it certainly isn't going to, again, apply to the fact that you might be getting a lot hotter.
Net force. You'll have multiple forces on objects as you go through this unit, and we will define those in the next video. But the sum of the forces equals your mass times your acceleration. Okay?
So that's not Newton's formula, just make it clear. Again, they wrote that in the 1800s somewhere. It's not Newton's math. It's not Newton's way of understanding the application of force as regards to quantity of motion, which is his word for momentum.
In a simple problem, if they ask for net force, they're just asking for this left side of the equation. You may start with a very easy problem.
I don't even know what that even means. They're asking for their equalities. You get either side. You have both sides. They can't. There's a 2 and a 2 on both sides, or a 4 and a 4 on both sides. There's no way to have something different on both sides.
That says, what is the net force if the mass is 5 kilograms, a 5 kilogram car, and it's accelerating at 5 meters per second squared? Well, your net force...
It's accelerating at 5 meters per second. There's no seconds squared. There's no such thing as a squared second. It's conceptual nonsense again. It's like the pull thing. You can't square or cube a second. Seconds, time doesn't have a volume of time. It's, you know, It's clearly just a linear, one-dimensional function.
Is 25 newtons. So let's talk about what unit this force is, because therein lies one of the things that we need to know. The force, believe it or not, forces are vectors. That means they have magnitude and direction.
So she's pointing out this vector thing versus the magical scalar that doesn't have direction. So it just has a magnitude, but it doesn't have a direction. So, so it's coming right for you. Oh, wait a minute, it's not. It's Angry Elephant, but Angry Elephant doesn't have any legs. So it's just Angry Elephant. I don't know. How do I even analogize such a silly thing as a motion, a speed, that doesn't have any direction? How can you possibly even say that stuff with a straight face? And again, you're doing it to children. I mean, it's just wrong to say something so nonsensical as, oh yeah, it has a speed in no direction.
All right, so a force is a vector, so it's going to have magnitude and direction. That means it can't.
Everything has magnitude and direction that has anything to do with motion. So it's impossible to have motion without magnitude and direction. So again, there is no such thing as any kind of scalar motion.
It can be negative or it can be positive depending.
So negative and positive is just, again, that's just an illusion. There is never any such thing as a cancellation or a direction that cancels some other direction or any of that nonsense. There's just motion in the universe, and it doesn't matter which way it's going because it doesn't ever truly cancel. If I crash two things, their fenders either crush, all right, and they show you how much energy they had, or if I make them elastic, uncrushable, then the energy is going to go somewhere else, and it's going to be most likely in the form of heat. Or I'm going to get some kind of beautiful reflection where all the energy just flies back. You still have an object going this way at the same speed. You still have an object going this way at the same speed. Newton's cradle. So if you let them reflect, no heat. If you don't let them reflect, lots of heat.
On the direction. The other thing that we need to know is that its unit is a mass. Well, you could actually tell me if I could talk to you in person. You could tell me because mass is a kilogram. We're not going to measure in grams in this. We need kilograms. Newton.
So there's no excuse for any of this talk, okay, about the whole idea that somehow this isn't one of that, when it's clear that the Newton is just the weight of 100 grams. It's not, you can convert it easily into just a pressure or a weight.
But it's put in kilograms, we measure in kilograms.
Yeah, but Newton said foot-pounds.
All right, so it's got to be in kilograms. If it's given to you in grams, do your dimensional analysis to get it to kilograms. Acceleration is what you could tell me. Acceleration, because you've been using it, is a meter.
So this is the part that's just wrong, okay? Times a second squared. There's no seconds squared involved. There's no meters per second squared. There's no such thing. Why are you making this up? Okay, there's no part of my acceleration has anything to do with squared seconds. My acceleration has to do with a certain amount of time it's going to take me to accelerate, and that's it. There's nothing else involved. And the acceleration really is just a change in my velocity, so it's really simple. I mean, it's my distance over a time, not a time squared. I mean, it's change in distance over change in time, not change in time squared. There's no squared function. So it's just cheating. And it's for the purpose of contriving Leibniz's formulation of motion in the universe. So the only way they can get to Leibniz from Newton is they have to square those seconds. They have to say something silly like per second per second. They have to cheat the truth. They have to cheat Newton.
Over a second squared. And that is our unit for...
Right, so it's not Newton's law. So I'm just saying Newton never wrote anything like that. Newton never said anything like that. This is not Newton's physics. Newton clearly said twice the velocity, twice the force. Twice the force, twice the velocity. a clear equality between the change in your momentum and the force hitting you. The force is essentially a momentum that you will absorb some portion of. Whatever portion of the force you absorbed, it will be equal to an amount of momentum.
Force. Mass times our units on acceleration, meter over second squared. Well,
so wrong again. There's no second squared. There's no second squared. There's no reason to put a second squared. It's not logical. There's no way to have a unit that's a second squared. It doesn't even say anything. 1 second squared. All of this is 1 meter, 1 kilogram. All of these units are in units of 1. Why would you square a 1? Oh, that's right. You wouldn't.
That's a big old pain to write every single time that you're writing your forces out, your unit. So we actually gave an honorary unit to this, and it's called a Newton.
Right, so it's an insult to Newton, actually, rather than an honor to Newton, because it's not his physics. Newton would never say kilogram times meter times second squared, divided by second squared. He wouldn't do it, because he knew gravity was 9.8 per 1 second. He knew it was 9.8 meters per 1 second per 1 second.
So either one are correct. You can call it a kilogram times meter over second squared, or you can call it a Newton.
You should be calling it a Leibniz, okay, because it's not Newton's physics or a Huygens. Call it a Huygens or call it a Leibniz, but you shouldn't be lying about what Newton believed, because Newton didn't fall for that crap.
Abbreviate that to a capital N. All right, so the unit would be a capital N. If you wanted the standard international, we call those, it's kilogram times meter over second squared.
Right, which again, you just keep drawing it as second squared. Why? What could this possibly be? 1 second. It can't be any other, it's not any number of seconds, right? We know a Newton isn't any number of seconds. So what does second squared mean? How could it possibly mean anything? Because we know this is a 1 second. You don't square 1 second. So you know that the only reason why you're writing it this way is that in some formulas you're going to want to put a 5 in front of that S and make it squaring the 5 and say there's 25 times the force when there's only 5 times the force. That's all you're going to use that little crappy squared for, is to cheat the truth.
All right, it is a vector. We're going to represent it by an arrow, just like we've been doing with all vectors.
And obviously, again, you know, so they're going to say that a train has a certain amount of joules of kinetic energy, and they're going to claim that somehow rolling down the track with its 5,000 joules of kinetic energy, it doesn't have a direction. So the 5,000 joules isn't going in a direction. Now, obviously, the argument is it has 10, joules of momentum. That if you were to convert it into foot-pounds, both of them, obviously the two numbers are going to be quite different. So momentum's going to say you have, let's say, 150 pounds of force. The kinetic energy theory is going to say you have 1,500 pounds of force. They're not going to get the same answer for the same amount of force.
The magnitude is going to be the tail of this thing, and the direction is going to be the arrow. All right, because they always have vectors, magnitude, and direction.
A joule is basically a kilogram weight, and a newton is 100 grams. So a newton is 1/10 of a joule.
Now, the other thing that you were going to look at is that on that magnitude and direction, remember I said it can be negative, and west and south are going to be negative.
So there's no such thing as negative motion, there's no such thing as unmotion, there's no such thing as anti-motion, ever. All of it has to be accounted for. If two things are going away from each other, you have to count both of them as things you have to account. You push this one with a force, you push this one with a force. You have to have a total force that includes both masses moving. You don't claim they didn't weigh anything. And the same thing, if they collide, you got to account for the force. Either they reflect and you keep the energy, or they don't reflect completely, and then you have energy in some other places like heat and deformation or pieces flying off or some other thing. You have to always account for the energy, the motion. The momentum always has to be accounted for. So there's no such thing as saying this thing undoes this thing. That these motions subtract each other, that you can have a piece of dynamite explode and this piece undoes this piece, and now there's zero energy in the universe. It's nonsense. And you shouldn't be teaching it to kids.
Again, north and east are going to be positive. Up is going to be positive. Down is going to be negative. All right, that's the second law now. So now we're going on to number 3. Newton's third law says for every action, there's an equal and opposite reaction.
So use all the examples that don't fit the law, and then explain how Newton didn't know about those things. So in Newton's world, a cannon can only produce, okay, the amount of the recoil, that is the mass of the cannon and the boat being turned, all of that will equal the amount of quantity of motion that the cannonball has. Their physics, Leibniz's physics, says the cannonball has 1,000 times more energy than the recoil energy. So there is no equal and opposite. Somehow the same gunpowder made more energy that way in the cannonball than it made in recoil of the heavy cannon and the heavy boat. So when the force hits heavy things, it doesn't make much energy. When it hits light things, it makes exponentially, well, quadratically increasing energy. So why are you teaching a third law that your own physics says isn't true? That there's a ton of examples that don't fit the third law at all. Every single time I take energy from a heavy thing and give it to a small thing, I'm going to be making free momentum, just a fact, by your theory, because there won't be an equal and opposite reaction. So I could ask the simple question, do you believe, okay, what moves a rocket ship when the exhaust flies out? What's going to move this rocket ship? The calculation of the kinetic energy? Is that going to move the rocket ship? I'll have an equal and opposite reaction to the kinetic energy. So I got a whole bunch. I got 2,000 joules of kinetic energy. Am I going to get 2,000 joules worth of force applied to the rocket? Am I going to get my equal and opposite reaction? Or is the truth that there's only going to be 100 joules of, did I say 1,000 before? Right? I'm going to get 10% of that as momentum in the thrust, and that's the number that's going to move this thing. The momentum is going to move the spaceship. The calculation of the momentum I push the other way is going to decide how fast this spaceship moves. And that's going to be true in space, and it's going to be true lifting off, and it's going to be true always. 8-pound bowling balls going 16 miles an hour do not have twice the energy of 16-pound balls going 8 miles an hour. And you're teaching the opposite, and it's not true, and you don't have any evidence that it's true. You shouldn't be teaching it because it's just plain wrong. And you're doing it while you slander Newton, even though you went to his house, and you're still dissing him.
All right, you've seen that and you've heard that so many times, probably.
Right, and it's just simply not true. Your physics says exactly the opposite is true. That I can create lots of mechanisms where I'm going to get a ton of energy going one way and no energy going the other way. No equal and opposite seen at all.
People like to use that as a saying. What does that mean? It means as I am standing here, I am pushing down on the floor with an equal force that the floor is pushing up on me.
Well, and again, you picked the wrong example, just in the sense that obviously that's a system in equilibrium. So, you know, that's cheating.
So I don't fall through the floor, I don't get thrown up in the air. If I push on this wall, I'm pushing on this wall, but I'm not falling through the wall because the wall is equally pushed.
So throw something at the wall. Throw something at the wall. Because that's when you're going to have a mass and a velocity. Okay, then you're going to have a real momentum to talk about. And then you're going to pervert that momentum into some extraordinarily high amount of energy. Okay, and momentum's going to say it's 10% of that amount of energy. So whatever you calculate to be the kinetic energy, it's always going to be 10% wrong, because frankly the force is in newtons, it's not in joules. Joules is complete nonsense in the sense that if you're going to calculate it with a velocity squared. So go ahead and do the calculation for the pen. Throw a pen at the wall, do the calculation, right? The kinetic energy is going to be a number 10 times bigger than the momentum number for the calculation. That's automatic. What is the wall going to receive? And what did you give away, right? Because again, it's still, you're the one creating the motion in the pen, so you're going to get the opposite reaction. Well, what's your opposite reaction going to be? Kinetic energy? Or is your opposite reaction going to be strictly and only momentum? So the third law has to be qualified as it only applies to momentum, nothing else. You have to make that qualification, and then you have to explain why you don't think momentum means anything, because kinetic energy is everything and momentum is nothing.
On me. All right, if I push on this, well, if I hold this sign is pushing down on my hand, but my hand is pushing up on the
Sorry, same argument over and over again.
sign, because if my hand weren't pushing up, it'd be falling down.
It's not a contact, so do something that requires real contact, collision. I mean, the third law is really talking about collisions.
All right, perfect. The other thing that's really interesting to think about that is kind of mind-blowing, I like these light bulb moments that kind of blow your mind a little bit.
Oh, brother. A little personal thing in there. Okay. Fluffy kitty? Yeah, I'm trying to think of something. Totally unrelated.
When you are walking down the hall of your school, or
oh, brother, so you really are driving this home that you're trying to pervert the little young minds.
Walking anywhere, you are really, with your legs, you are pushing down and back on the floor.
Yeah, that's right, you're pushing. Yes.
You are going down the hall because the floor and friction are pushing you down the hall. In other words,
so that isn't, I don't think it's really appropriate to say the floor is pushing. You imposed on the floor just rebounded, okay? So it didn't really, it's not fair to say it's pushing you. You pushed into it, okay? And it didn't yield. It said, no thank you to your push. I mean, you're still going to go forward even if the floor yields to a point. Well, now you still, there has to be a rebound somewhere, or you just keep walking and not going anywhere.
So the two forces there are what you're doing to the floor, pushing down on the floor.
There you go. And the fact is the floor is just rejecting it.
And then friction and normal force, which we're going to talk about what those things mean in the catalog. But believe it or not, the floor is pushing you forward with the help of friction. All right, so
again, there's no separate thing called friction. Friction is just a transfer. So you can only lose energy to friction. There's nothing else friction is made out of except you having contact and losing your energy to the friction. Now, the opposite can happen in the sense I can have a conveyor belt spinning, and then we apply the friction and you get the energy instead. You take the energy from the conveyor belt and conveyor belt gives it to you. But that's all that's happening. Friction is just an exchange. So that's how it should be talked about. It's contact. It's like electrical contact. It's an exact parallel, frankly, between contact between electrical wires and how you're able to pull more energy, transfer more money, more force, the better the contact. So the more frictional contact, the more you can transfer, negotiate the differences you might have in your velocity. So more contact means you can make more exchanges to equalize how much money you have. Because that's what everything is going to try to do, is if they have enough contact, this thing and this thing are going to try to agree on, well, let's both have, I have $60, you have $20, let's both agree to have $40. That's the currency, is always looking for equalities.
Very weird to think about that you are, if you really think about how you walk, you're pushing down, right? floor is pushing up. And with help of friction, you get to go forward and down the hall. So interesting to think about that. All right, perfect. All right, I think that's it for our force. This was a very quick introductory of what a force is, Newton's 3 laws, which hopefully you've seen before, what the unit on that force is, and then...
So it's not Newton's law. So the whole second law is just a slander against Newton. Clearly, Newton believed force equals momentum. That's it. You want to know the rate? Then you can use time. How many seconds, okay, equals how much. So per second, what's the force? But if you want to just know the net force equals the net change in your momentum, period. Force equals momentum. All right.
It's a vector with magnitude and direction and will be either positive or negative. Thank you for watching.
So no such thing. It's a negative force. No such thing.
And happy physicsing.
Okay.
Hi, I'm Beth. And I'm...
Okay, so anyway. All right. So I almost feel like I've cheated the other Beth. We should probably play one of her videos too. But anyway, so this is it's one of these channels where they got 50 views or something, and they're making a reasonable effort. And the internet is dissing them in the sense that, yes, this might appeal to somebody, and they're just not going to get exposed to it. And the only way to even have some chance of finding it is you have to go through 56 million Hindi videos. And because you can't do a rational search on YouTube or Google or Bing. I mean, I tried all of them, and they're all polluted, by the people with the lie titles, the English titles for the non-English videos. I mean, it really should be something they fix, right? I mean, Google's big on science and all that kind of crap. Why are they letting the system cheat us that way? I mean, you really shouldn't be able to use an English title on a video exclusively in a language that's not English. I mean, that's just lying. So why do they let them lie? Anyway, I mean, I can go back 20 years ago on YouTube, and it was so much better. So you would always find channels. You could find new channels. You could find all kinds of stuff, and you can't find shit now. All you can get is new roads to the most popular videos, but nothing that'll take you to anything somebody might be doing better than one of those popular channels. They get to control the entire access to content on the internet is controlled by people like Veritasium, and they don't do anything to spread the love, so to speak. All right, so till the next time, and such and so forth and whatnot. I can do this. This has been DraftPhysics.com, DebatePhysics.com, but again, people won't debate. They won't argue the actual argument. They won't argue the evidence. They won't show any evidence. It's just really dismal. And this is science. Science that's afraid of arguing evidence and experiments. Well, they're afraid because they don't have any. Again, the simple stuff. 5-ton train going this way, right? 10-ton train going 5 going this way. So I have a 5 going 10, okay, going this way. And I have a 10 going 5 going this way, and I just tie them together, right? This is such a simple experiment, right? You could just have a spring to launch them, and you'll automatically get that result. The 10 mass will go half the velocity, the 5 mass will go twice the velocity. Automatically get it. So I just put a spring between them, release them, and just have a string tied to both of them. The string runs out, and what do you think happens? Do you think the 5 wins? This was the 10, right? You think the 5 wins and it drags the 10 with it? Is that what you think happens? Because the 5-ton going 10, the kinetic energy theory says it has a scalar magnitude that is twice as big as this. So why can't it use its scalar magnitude to pull this with it? Oh, that's right. Because it doesn't have any scalar magnitude. Because it's all nonsense. It doesn't happen. It's not the truth. It's all nonsense. It doesn't take 25 times the fuel to spin something 5 times as much. It's a stupid, idiotic theory invented by a kook. And here it is 350 years later, and these people who think they're educated, okay, can't figure out that they're talking shite. Amazing. Amazing that I am the only person on the YouTube, on the internet, that's capable of making this simple observation that you chose the wrong theory, that Newton was right, Leibniz was a stupid putz, who actually tried to get Newton thrown in jail. I mean, that's the truth of it. He really did try to get the king to sanction Newton, put him under house arrest, stop him from publishing, because he was spouting this atheist theory. Amazing bullshit. So, come on. Do better. So I'll just do this to every single physicist on the internet. I'll just go to their channel and I'll say, come on, you're teaching this garbage. Why are you teaching garbage? I mean, you can know it can't be right, right? I mean, I think they can know, right? Beth, you can know that 5 mass, 10 velocity, 10 mass, 5 velocity. The 5 mass isn't winning. You're not going to knock down more bowling pins with an 8-pound ball going 16 miles an hour versus a 16-pound ball going 8 miles an hour. It's not going to happen. The pins are not going to respond to the kinetic energy because they're not going to be able to see it. They're not going to know it exists because it's a fable, and the pins are smart enough to figure out it's a fable. The stupid bowling pins are smarter than... The pins can figure out it doesn't exist, and you can't? Come on. Do better. Ah, enough of a video anyway, so throw it in there. I'll do the other guy too. I mean, there's nothing else to do, right? There's no other way. Physicists have to fix physics. You can't fix it from the outside. They have to fix it. And they just won't do it. They won't tell you that their pope is wrong about something. They'll just say, no, the Bible is literally true. I'm told I have to say it. You know, and I'll just preach out of this stupid, archaic pile of nonsense. Shit.